So in the non-inverting amplifier, so what we are going to do is we are going to give the input to the non-inverting terminal, that is the positive terminal of the op amp, and the inverting terminal, that is the negative terminal, is grounded. Okay. And one more thing you have to remember, even though the non-inverting terminal is grounded, the feedback has to be given to inverting terminal. Even though the inverting terminal is grounded, the feedback has to be given to the inverting terminal only. Always, please remember, in op amps, we have to give the feedback connection to the inverting terminal. Never give it to the positive terminal. Why we are going to give the feedback to the inverting terminal, I have told in the last class only. So we are going to give feedback to the inverting terminal in order to reduce the gain or to adjust the gain. If you give this feedback to the positive terminal, what happens is the gain further increases. Already the practical op amps, the gain is considered to be 2 into 10 to the power of 5. Again, if you give the feedback to the positive terminal, then it will be greater than 2 into 10 to the power of 5. So we don't want that much high gain. We want normal gain, and based upon the applications, the gain has to be adjusted. In order to adjust that, we have to give negative feedback. So negative feedback is the one which is obtained when we are going to connect the output with the input, because the definition for the negative feedback, what we tell is, the negative feedback is the one where the input and output are out of phase. The positive feedback are the one where the input and the output will be in phase. So here we know that when you consider the inverting terminal and the output, they're inverse of each other. Whatever you give here, that will be inverted and given out at this point. Okay. So but when you connect the feedback to the positive terminal, then the output and input will be in phase. Output and input will be in phase. So that's why, and the whenever you connect the feedback to the positive terminal, automatically what happens, the gain further increases. It adds some gain to the existing gain. But here, if you are going to consider the feedback to the inverting terminal, during that time, it is going to reduce the gain. So by properly designing RF and R1, we can reduce the gain or decide the gain. Because see, the op amp is an amplifier which can be used for different application. We might use it for a loudspeaker, we might use it for a small mobile phone. So where the amount of amplification required is entirely different. In a loudspeaker, the level of amplification required is very high. At the same time, the level of amplification required in a mobile is less. So based upon the requirement, we have to change the gain. So we need to have that flexibility. So to have that flexibility, we go for the negative feedback. So we will be adjusting the feedback. The gain. So by adjusting the feedback resistors, RF and R1 are the main two resistors which plays an important role in adjusting the gain. So now as we are starting with non-inverting amplifier, non-inverting means positive terminal. So positive terminal will be having the input and negative terminal will be grounded. So now as you can see that since we are giving input to the positive terminal and we are taking the output across this terminal. So output, it is the input signal and this is the output signal. You can see both are in phase. There is no phase difference between them. In our earlier case, what we studied in the last class, they were out of phase because the input was given to the inverting terminal. Always remember, whenever we are going to give input to the inverting terminal, then the output will be having a phase difference of 180 degree with respect to the input. Or in layman's language, output and input is the reverse of each other. Okay, you can see there is positive terminal is like this, but at the output you get it as negative terminal. I mean negative terminal output. Here you are getting the negative phase, you are getting positive phase. There positive phase, here you got negative phase. So that is the reverse of each other. But here you can see that the positive phase is written as it is, negative phase is written as it is. So here there is no change in phase. Even though you are giving the input to the positive terminal, the application of Kirchoff current law will be always to the virtual ground. Please remember, whether you give the input to the positive terminal or negative terminal, the Kirchoff current law has to be always applied at to this junction. This junction is known as virtual ground. So to virtual ground only we have to apply. We have to consider the virtual ground or the node for the application of Kirchoff current law. Because Kirchoff current law is defined by considering a node or a junction. So current entering a junction is equal to current leaving the junction. So we have to consider that. So here let us assume the current here is I1, which is coming in this direction. So even though practically speaking, there will be no current which is flowing here because it is grounded. But we will take the conventional direction. Then we'll assume that there is the current will flow like this. Because whenever since it is connected with the feedback, so here V1 will, according to virtual ground concept, the voltage across V1 will be equal to voltage across Vi. Because of this V1, there will be some amount of current which is flowing towards R1 as well as RF. Okay, but here, according to the conventional direction, we will be just giving the direction like this. Just remember that. So now current entering is equal to current leaving. So current entering is I1. So current entering is I1 since it is starting from the ground to this V1. So it is 0 minus V1 because this is ground, it is completely 0, and this is V1 divided by R1. We are writing current in terms of V by R, voltage by resistance. Coming to I2, so I2 is the current which is flowing through the feedback resistance. So V1 minus this point is V0. So V1 minus V0 divided by RF. So divided by RF. So after that we have to rearrange this, and always in these derivations we prefer to have an equation with respect to the output. So rearrange these equations, whatever we have got, and write the equation in terms of V0. So when you rearrange this equation and write the equation, we get the rearranged equation will be V0 is equal to V1 into RF into 1 by RF plus 1 by R1. Then what I'll do, I'll take RF inside this bracket. When I take inside this bracket, then I'll be getting here V1 into once I take entire things inside. So we'll be getting V1 plus V1 into RF by R1. Again, I take V1 common. So V0 is equal to V1 plus V1 into 1 plus RF by R1. So this is our, this V1 is our input. So V1 is our input and 1 plus RF by R1 is our gain. If a question is asked on what is the gain of non-inverting amplifier, then the gain is 1 plus RF by R1. If a question is asked that what is the gain for inverting amplifier, Suraksha, what is the answer?
Output by input.
That is very general formula. I'm asking with respect to inverting op-amp, what is the gain? So what is the gain we have? RF by R1. By properly designing RF and R1, we are getting the gain. The general formula is output voltage is equal to gain into input voltage. This is the general formula. All the formulas, all the derivations, whatever we do, it will be in this format only. You'll be having input voltage and you'll be having gain. And negative sign indicates we are giving input to the inverting terminal. So gain of inverting op amp is RF by R1. In the same way, what will be the gain of this? It will be 1 plus RF by R1. If a question is asked on non-inverting amplifier gain, then the gain is 1 plus RF by R1. Suppose let us, and next we know that according to virtual ground concept, V1 is equal to Vi. According to virtual ground concept, V1 is equal to Vi. So in the place of V1, we can put Vi. So V1 is equal to Vi. So we'll put Vi here. 1 plus Rf by R1. So 1 plus Rf by R1 is a gain of an amplifier. So output is in phase. Output is in phase means the output and input, there is no phase difference. Therein, they look same. During the positive phase, we are getting positive phase, and during negative phase, we are getting negative phase. After this, the next one is inverting adder. Till now, we discussed about single input. Single input getting amplified whenever it is given to the inverting terminal and whenever it is given to the non-inverting terminal. Now, if suppose multiple inputs are being given and I want to add these multiple inputs and amplify them. So then how I'm going to do is, you can do it in two ways. One is taking the multiple inputs to the inverting terminal, add them and amplify them. The other one is take this multiple inputs to the positive terminal or non-inverting terminal and do the same task. But doing, adding the n number of inputs at the negative terminal is easier compared to adding n number of inputs to the positive terminal. With I am talking with respect to the mathematical analysis. In analysis, inverting adder is easy compared to the non-inverting adder. So why it is complex, we'll discuss it when the concepts come. So now the inverting adder, here what we are doing is we are taking three inputs. Now the three inputs have to be added up. In our earlier cases, we had a single input, we were doing it easily. Now we have three inputs. The three inputs have to be added and given to this for this point. And after that, the sum of these three inputs acts as input. Some of these three different inputs will be acting as input. That input will be amplified and given out. This is what we have to do. So same way we have a feedback resistance and R1, R2, R3. These are all individual resistance, whatever we are having for input, different inputs. Now again, Kirchoff current law will be applied. So current entering. So this junction is always the virtual ground junction, whatever we have, the same junction we are going to consider here also. So the current entering at this point is equal to current leaving. So current entering is what I1 is entering, I2 is entering, I3 is entering. And current leaving is what IF only. Why we are not taking the current which is entering this op-amp? See here the current which is here also there is one connection. Why we are not considering that one? Tejaswini,
Sir, because it's very low and negligible.
why it is negligible? Because the input impedance is very high. So input impedance is in terms of mega ohm, as we have already discussed the characteristics of an op-amp. So when the input impedance is very high, automatically the current entering also will be very much negligible. So we just assume it is almost zero because it will be in terms of micro and nano amperes, and here we are talking with respect to milliamperes. So when I consider nano amperes with milliamperes, it is very negligible. So the current entering is equal to current leaving. So during that time, we'll just ignore the current here, which is entering to the op amp is negligible. So IF is equal to I1 plus I2 plus I3. So IF means the current which is entering from this point to this point. So this point, according to virtual ground concept, we know that since the non-inverting terminal is grounded, this voltage will also be grounded, acting like a ground. So voltage at this point will be equal to the voltage across non-inverting terminal. The non-inverting terminal is grounded means the non-inverting terminal will be having zero voltage. So this also will have zero voltage. So 0 minus V0 by RF. I1. So I1 means I1 is the current which is coming from V1 to this point. So V1 minus 0 divided by R1. So it is just the Ohm's law, I is equal to V by R. But when we want to find out the current which is passing through the resistance, then we have to take the potential difference among the two terminals of this resistance. So that's why we take the voltage at this point and this point. We take the difference of these 2 points. That will give you the voltage across R1. So V1 minus 0, V2 minus 0, V3 minus 0. So after that we get this one, and we know that we always prefer to write the equation in terms of V0, and that is what our intention is. So V0 is equal to minus RF, V1 by R1 plus V2 by R2, V3 by R3. Suppose if I am going to assume all this R1, R2, R3, the input resistances values are R. So that's common. Then what happens? R1, R2, R3 becomes equal and we substitute as R. So if I take it outside, I'll get V0 is equal to minus RF by R into V1 plus V2 plus V3. So here, what is V1 plus V2 plus V3? This is our input. What is RF by R? This is our gain. Why this negative? Why we have this negative symbol, Sudeep?
Yes, sir.
Yeah, why
Can
we
you
have
repeat it?
this negative symbol here? What does this negative symbol indicate? What does this negative symbol which has come here indicate?
Sir, because here the output is considered as virtual.
Mm-hmm. No. What I told from the beginning, when you will consider negative, when you will consider positive, just see the circuit. Rohan, Rohan, Pranav.
Yes, sir.
Yeah,
Am I
can you answer this question?
uh,
Why we have
uh,
negative at the output? Minus. What does this minus in the output represents? Does it represent the gain is negative?
um,
What does it represent? I have told this. What does it represents? Many times I have told. Can anyone answer this?
Output is inverted with respect to the input signal.
Yeah, output is inverted with
Inverter.
respect to the input signal, because the name itself tells we are telling inverting. Whenever the name inverting comes and whenever you are giving input to the negative terminal, then output and input signal will be inverse of each other. That is what minus sign indicates. The output is the inverted form of input. If you are giving a sine wave, the output will be just the inverted form of that. That is what minus sign indicates. RF by R indicates the gain. V1 plus V2 plus V3 indicates the sum of the inputs. After this, we are having the non-inverting adder. So in the non-inverting adder, you can see that here the uh, 2 or 3 inputs will be added at the non-inverting terminal. So here we have, just for an example, I have considered 2 inputs, V1 and V2. So this V1 and V2 will be added and given. So but here we know that always what we do is we are going to we will always apply the Kirchoff current law to the virtual ground of the which is present at the inverting terminal. So that's why what we have to do now is first we have to find out what is this total voltage which is coming at the point B. And after finding out the total voltage because of V1 and V2, then we'll apply the Kirchoff current law at A, then we substitute that the voltage across A will be equal to voltage across B according to virtual ground concept. So this is what we have to do. See, the method is similar to what we have done in the non-inverting amplifier, but here we are having two. Instead of having a single inputs, we are having two inputs. The two inputs have to be added first, and you have to find out what is the voltage coming here. After that, we have to tell according to virtual ground concept, VA is equal to VB. Then after that, applying Kirchoff current law at VA, we get I is equal to IF. After that, the same thing, whatever we do, the same method we are going to follow. So now, at the beginning, in order to find out what is the voltage across voltage at this terminal B, so we have to find out the sum of these two. So I think now it will